So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to talk about basic integration, that is, chapter number 2. Because in our previous video, we have done the differential calculus as a chapter number 1 of this book, right? So I hope you have watched that video completely, and now it's our time to just let's just walk away from differential calculus to integral calculus, right? So basically this chapter will deal with basic integration. You know what, guys, before beginning the chapter, let me just say something here. We have done a lot of things so far, like we have done integrals, basic, mid level, advanced level. So we have done almost all of these things, right? But I have never talked about what is integration, right? And that is what this video is all about, right? So yeah, you know my philosophy. If I'm gonna use anything, so I need to know why I'm using this. Is there any way, any other way, right? So yeah, for that case, we have to just look for basic integration, right? Okay, so I think it's time to just get into the chapter, right? Okay, so let's just get back to the chapter, and we have basic integration. So can you imagine that this book discusses integration from this sign, from the symbol, not sign actually, but from this symbol, from this very symbol. So yeah, you know what, when I was in 11th standard, so I just got to know that there is something called, oh, not 11th standard, but I got to know about integration in 10th standard, right at that time. I was quite curious about mathematics, so that's why I just got to know. Like, I was curious that what is in 11th and 12th standards mathematics. So I just got to know that there is something called integrals, and I was loving to just write this symbol. I think I should use ball pen instead. So yeah, that was kind of amazing. So yeah, this was. So yeah, this is amazing. So basically, in this chapter, we will explore and review basic integration techniques such as U substitutions, integration by parts, partial fraction decomposition. We'll try to apply these methods creatively to a collection of elementary yet unique problems. With that in mind, let's get started. Yeah, amazing. Take a look at this. The notation for the indefinite integral is this. Was introduced by Leibniz in 1675. He adapted it from an archaic form of the letter S. Wow. So basically, this was S, but we just then he just wrote it down something sort of this, and then he come across something sort of this, and finally it's this. Wow, that's kind of amazing, isn't it, guys? Okay, so I think we should not waste our time here. Okay, so we have the first things first, that is the Riemann integral. Okay, let's just talk about the definition. For a function f of x that is continuous on the interval, open interval a comma b, we can divide the interval into n subintervals. Yeah, we'll talk about this in detail, don't worry. Each with length del x, and from each interval choose a point x sub k. The definite integral is done. Okay, so this is the definite integral, right? So basically your indefinite integral doesn't have any kind of limit actually, but when you talk about definite integral, so you have a as your lower limit, and this is your upper limit, right? Upper limit actually, and this is your function which you are going to integrate, and yeah, with respect to what, right? So that shows that the derivative factor, you can say. So basically the integral, you know what, guys, in simple language, basically this is area. That's it, right? So limit n tends to infinity, the sum as k goes from 1 to n of f of x sub k times del x. This definition, provided by German mathematician Bernhard Riemann, expresses area as a combination of infinitely many vertically oriented rectangles, a technique known as Riemann's sums. As the rectangle gets thinner, del x is 0. So basically this is your width of the rectangle. The total area of rectangles approaches the value of the integral. Yeah, obviously. So yeah, that's what I was talking about. So just take a look at this. What I'm gonna do here is I need to use a straight line instead, and I'm just gonna drop it down something sort of this. Wait a second, let me just get finished with this and then we'll talk about. Yeah, I'm done with the rectangles actually. So let me just zoom in a little bit and then I'll just show you that. So just take a look at this. When though it's a lot of like you can say it's like the distance between these two things is extremely high, but we have to talk about actually this is infinite rectangle. I'm sorry, this is finite rectangles, right? But we have to make, or you can say we have to imagine or visualize infinitely many rectangles in this only area. So can you imagine? So basically you know what, when we talk about infinitely many rectangles, so the width of them would be so less, actually would be extremely low, that will be tending to zero only, right? Yeah, tending to zero only. But and if we talk about well, at large level, you can say that the curve is something sort of this, but actually the this this you can say this length can be considered as a straight line, right? So basically this is a straight line for them, and somewhere this distance will matter, like this distance, the length will matter, but this length will not matter. What I'm talking about is the difference between two consecutive lines on this curve won't matter if we would be having infinite number of rectangles over there. So that's why I just made all these lines to just explain you that, right? So yeah, that's really amazing. And you know what, just take a look at the formula here. We have this sum of, this is your, what is this function, right? This is your function. So basically this is your curve and this is your width, right? So basically this is your y and this is your x, right? And when we just multiply both of them and add all these rectangles, multiply the area of one rectangle and add all these things up, so basically that's going to be giving us the area of this part. Just imagine that. And that is what it is actually, because n is tending to infinity, so that's why there is an n tends to infinity. Though you can write this as the sum as k goes from 1 to infinity of f of x sub k del x as well, because obviously you can just plug this back over there, but it's all right. It's kind of good to just take a look at that. So yeah, so that's how you can understand. Basically this is your area, right? Okay, so I hope you are done with the basics of integration. So basically this curve is your for x squared, right? In the interval of 0 and 1 actually. Okay, so yeah, just take a look at this actually. So this is what I was talking about, graph of the midpoint Riemann sums for y equals x squared on with only two sub intervals. So yeah, so basically sub intervals is I think this one. So yeah, it's kind of easy to understand all these things. Yeah, just take a look at this. It's kind of it's kind of looks something sort of stairs, right? So basically, and when you talk about infinitely, because look, just take a look at this is also a rectangle, right? So basically this is finite number of rectangles over there. But if we talk about infinitely number of rectangles, so obviously it's the distance would be immensely low, and therefore we can say the distance between consecutive two rectangles would be nearly same. So basically the area of all these rectangles would be same, and that's why we just add them up, and we would be getting the area of the curve, right? Okay, so we have Lebesgue integral. Lebesgue, I think I'm pronunciating it correctly, I'm not sure, and correct me down if I'm wrong here. So let's just read this out once. The Lebesgue integral is another definition of the integral proposed in 1904 by the French mathematician Henri Lebesgue. The formal definition of the Lebesgue integral involves measure theory, which is beyond the scope of a book. Oh, wait a second, I'm not sure about this measure theory. So, okay, a helpful intuitive picture of the Lebesgue integral can be given by thinking of the Lebesgue integral as talking the areas of horizontal rectangles. Okay, wait a second. Here we have talked about the vertical rectangles, but I think this Lebesgue integral definition is kind of talking about the horizontal rectangles instead of the vertical rectangles one encounter in the Riemann definition. So yeah, in the Riemann definition we have talked about the vertical rectangles, but in the Lebesgue integral we are having horizontal rectangles. So yeah, it's kind of interesting, isn't it? So I think this book doesn't talk about that much of the Lebesgue integral, because it's kind of measure theory, and he legitimately says that no, we cannot talk about that in a single book. So okay, let's just leave this out. Though if you request me, then if you want to know about that thing, so just tell me, I'll just talk to you. I'll just get a video of that as well. So yeah, so now we are heading towards the use substitution that is written over there as well. Okay, oh wait a second, we know about that, right? Okay, in our previous video, as if you have watched that, so we have proved this identity, and this is kind of amazing, isn't it? So let's just talk about the proof that is given in this book as well, which we haven't seen there, but yeah, it is given over there. But I have proved this by myself in that video, so if you want, please check that out. Okay, so we have this integral, right? So now you just let x equals a plus b minus t, so dx is going to be minus dt. So basically that's going to be something sort of looking like that, and there, using this negative, you can just switch up the order of the limits. So basically that's going to be giving us your I equals this, the integral as, I'm sorry, integral, wait a second, yeah, so integral from a to b of f of a plus b minus t dt, right? And that's how you can just basically this is a definite integral, right? So you can just replace this t with x, it doesn't bother, right? So yeah, so therefore you can say your I, basically your integral from a to b of f of x dx is equals integral from a to b f of a plus b minus x dx. So yeah, that's kind of amazing, right? Okay, we have example 1 here. This integral, we just have to evaluate this down using the same stuff. We are having your upper limit as pi, and this is your upper limit, and this is your lower limit, right? So we can write this as integral from 0 to pi using the property that we had proven here. It's pi minus x sine of pi minus x over 1 plus cosine squared of pi minus x dx. And cosine of pi minus x is just cosine squared. I think cosine of x, wait a second, let me just calculate this here. So it's cosine of pi cosine of x minus sine, I'm sorry, plus sine actually. So yeah, it's gonna be cosine of x only. And if we talk about sine of pi minus x, so it's sine of pi cosine of x minus cosine of pi sine of x, right? So Yeah, so here we have sine of pi is 0, right? And cosine of pi is -1. So basically this -1 and times negative is going to be giving us positive. So basically it's coming out to be sine of x only. So our integral becomes integral from 0 to pi of x sine x dx over 1 plus cosine squared dx x dx actually equals integral from 0 to pi of pi minus x sine of x over 1 plus cosine squared of x dx, right? And we can just write this as integral from 0 to pi times sine of x over 1 plus cosine squared of x dx minus integral from 0 to pi x sine of x over 1 plus cosine squared of x dx. And guess what, this is your I, this is the same integral. So basically we can add both sides with that integral. So basically we would be having 2 times integral from 0 to pi of x sine x over 1 plus cosine squared of x dx, and we have pi is a constant, so integral from 0 to pi of sine of x dx over 1 plus cosine squared x, actually cosine squared x, right? Okay, and now we have to evaluate this integral, and this is kind of easy because you have to plug cosine of x equals t, so that's going to be giving us sine of x dx equals dt, right? And if we talk about limits, so basically cosine of 0 is 1 and cosine of, wait a second, the derivative of cosine is, I think, wait a second, I think, yeah, I did a mistake here because the derivative of cosine is minus sine of x, right? So basically this integral is gonna be pi times integral from 1 to -1, and we have dt over 1 plus t squared, and we can write this as 2 pi integral from 0 to 1. Basically we have negative dt, so basically that negative just helped us to switch the order, and since the function is an even function, so we can just multiply the integral with 2 and write the integral from 0 to 1 instead of from -1 to 1 actually. And we have 1 over 1 plus t squared dt, and this is quite easy because it's arctangent of t from 0 to 1, and we are having 2 pi, so arctangent of 1 minus arctangent of 0 is just 0, so arctangent of 1 is pi over 4, right? So we have pi, we are coming out to be pi squared over 2, right? So basically 2 times integral from 0 to pi of x sine x dx over 1 plus cosine squared x is coming out to be pi squared over 2. So dividing both sides with 2, so that's going to be giving us here 4, because we were having a factor of 2 in front of the right integral on the left hand side. So I think the value of this integral is coming out to be pi squared over 4. Let me just check this out once. Yeah, so here it is. Okay, so let's just talk about, so yeah, he did the same stuff actually. Yeah, so what he did, he just added up, and so here you just got rid of these two things, having only pi term. So yeah, we just having this one. Yeah, so it's kind of easy, right? Okay, yeah, this integral, I did this integral in the previous video, so you can consider watching that video, right? Because I have done a lot of things which is given on the second chapter, the proof of that thing on the second chapter, but it was shown in the first chapter, so that's why I just did all the proofs as much as I knew on the in the previous video on the first chapter only. So yeah, and even though I did this one as well, so yeah, you can check out the solution, but the way I did was amazing, and I think the way, this is the way I did, as much as I remember. Yeah, okay, so yeah, you should watch that video. And again, this integral, you just have to go with that method only, the way we did the first integral in this video. So what I did is just use the property, right? And we know that cosine of pi minus x is just cosine of x. Wait a second. Cosine of pi minus x is cosine of x, and we have sine of pi minus x as sine of x, right? So we have, yeah, so the way we did here, yeah, it's kind of same stuff, right? And this is the curve actually. So that's why I admired this video in the very beginning of the previous video, because this book is kind of amazing, and it's made for everyone who wants to learn mathematics. So yeah, they can consider this book. So we knew that we would be reaching up to here, and from here we have to, here you have to you have to put u equals tangent of x in order to get secant squared. Look, you know what, you were having integral from -1 to 1 of du over u squared plus 1 whole squared, and this can also be written as integral from 0 to 1 2 times actually du over u squared plus 1 whole squared actually. So when you plug u equals tangent of x, so du is gonna be secant squared of x, right? So basically we have 2 times integral from 0 to, not 1, I'm sorry, it's when you plug u equals 1, so it's pi over 4, and we have secant squared of x dx over tangent square plus 1 is just secant squared, so we have secant to the 4th x in the denominator. So basically we are having 2 times integral from 0 to pi over 4 of cosine squared of x dx, and here we have to use a double angle formula of the cosine squared of x, actually cosine, so that's how you can just so yeah, it's kind of amazing. And I won't say these integrals are difficult to do, but still I can confidently put them in the middle category. They are not that much basic as well. Okay, so we have got the integral from 0 to 1 of natural logarithm of gamma of x. So this is kind of amazing, right? And basically there is a standard way by which we usually do this integral. So the standard way, I'm just gonna let you know that standard way here. Standard way. So basically we have learned that integral from a to b of f of x dx equals integral from a to b of f of a plus b minus x dx, right? Okay, and here, so okay, so basically we are having integral from 0 to 1 of natural logarithm of gamma of x dx, and using this property, right, we can write this as integral from 0 to 1 natural logarithm of gamma of 1 minus x dx. And whenever you see, just take a pause here, and whenever you see gamma of x and gamma of 1 minus x simultaneously, then what you have to do is to use Euler's reflection formula. I have proved this thing, so you can consider watch my proof, because that's amazing. So basically Euler's reflection formula states that gamma of z times gamma of 1 minus z equals pi over sine pi z, right? So okay, wait a second, let me just go through the solution of him. And here's the curve of natural logarithm of gamma of x, not just gamma of x. Yeah, theorem. Though this book haven't discussed this formula yet. I'm not sure about the rest of the book, but so far I haven't seen the proof of this thing in this book. But yeah, Yeah, oh wait a second, I just got this c 9.3 for the proof. Okay, I cannot defeat you, the author. I think it was Hamza El Zamiri. I respect you, sir. I love you. Yeah, so he just provided the proof of this as well, so we'll just see that. But it's in the ninth chapter, I think, right? Okay, so using the formula, so basically cosecant is just 1 over sine. So yeah, you might be knowing that, right? Okay, so yeah, so that's how you can reach up to something sort of here, because added up. So yeah, and now it becomes quite easy. And you know what about this integral? It's just the integral that we have seen in our previous video. I'm sorry, previous integral. That is where it is. Wait a second. So this was, yeah, this was, you know what, for that case we were having integral of natural logarithm of sine of pi z dz. So basically you have to put pi z equals t, and that's then how you can just get back to this point. So yeah, let me just show you that. I think it's done over there. Wait a second. Yeah, here we are. Yeah, just take a look at this. U equals pi times x. So that's how. And again, you know what, integral from 0 to pi equals 2 times integral from 0 to pi over 2. This, I have discussed this thing as well in my previous video, and that's why I'm just forcing you all to just watch that video once, please, because I have done a lot of things in that video. It's kind of 1 hour video, so for that case, and literally I haven't wasted any moment in that video. Please just please believe on me. Okay, and now, so finally we are having the result as natural logarithm of 2 pi over 2. Yeah, okay, now we have, yeah, we are having a couple of integrals. So that's the thing. And here we know about this integral. We have talked about this several times in our previous video, and we have got double integral, something sort of there. So yeah, you can just check out the solution if you want. But yeah, this book talks about a lot of things, right? Again, an integral, right? So yeah, so we just discuss this integral. Let me just go through this integral once, and then we'll just talk about this, because this looks quite amazing. Okay, let's just discuss that integral. Wait a second, let me just get a sip of water, and then we'll just talk about this. Okay, so let's just talk about this. Okay, so we have integral from 0 to 1 of natural logarithm of cosine of pi x over 2 over x squared plus x dx. So it looks ridiculous at first, I would say, not because I saw the solution, but because I can see the depth of this integral as per my experience. Okay, so this is the curve, or this is the graph of our integrand, that is this thing. I think these all graphs are made by Desmos, I'm not sure, but mostly it's done by Desmos only. We have factored it out as x times x plus 1, right? And what we have done, okay, wait a second, you know what guys, if we are having 1 over x times x plus 1, so this can be written as x plus 1 minus x over x times x plus 1, right? And now we can split it up as x plus 1 over x times x plus 1 minus x over x times x plus 1, and here we would be having 1 over x minus 1 over x plus 1. So basically that's what there we have done there, right? Actually the author had done there. I didn't. Okay, using the trigonometric identity, yeah, this is, we know about that. Yeah, okay, so we have okay, wait a second. So basically now we know that sine of 2x is 2 times sine of x cosine of x. And now what we have to do is to replace x with pi x over 2. So we have sine of 2 times pi x over 2 equals 2 times sine pi x over 2 cosine x pi over 2. And isolating cosine of pi x over 2, so that's going to be giving us sine of pi x over 2 times sine of pi x over 2. So that's what it's written over there. So yeah, okay. So we have done this thing so far here. We haven't did the same thing in the second integral. Okay, and now we can use the natural logarithmic property that says natural logarithm of, wait a second, natural logarithm of a over b is natural logarithm of a minus natural logarithm of b. So your a is sine of pi x and your b is 2 sine of pi x over 2. So for that case we can split this integral into two separate integrals as well. So basically we are having three integrals now to solve them out. Okay, and we have assumed it as the first integral and the second and third one, right? Okay, wait a second, wait a second. Okay, so basically he used the identity that we have proven so far, that is integral from a to b. Wait a second, integral from a to b of f of x dx equals integral from a to b of f of a plus b minus x dx. So yeah, and you know what, we have sine of, okay, so yeah, we have sine of pi over 2 minus pi x over 2. So this can be expanded as sine of pi over 2 cosine of pi x over 2. And you know what, cosine of pi over 2 is 0, so we cannot consider that one. So we are having, and sine of pi over 2 is 1. So basically this part is coming out to be cosine of pi x over 2, and that's why we have this one over there, and we have same integrand, right? Okay, so obviously the limits would be changing over there because we have done something there, right? Okay, and now yeah, okay, so yeah, it's kind of useful, you can say. Okay, so we have integral from -1 to 1 of natural logarithm of cosine of pi x over 2 over x plus 1. Okay, and now we substitute u equals x plus 1 plus x. Wait a second, where? Okay, so actually here in this integral. Okay, so that's gonna be giving actually cosine of pi over 2, and we have x equals u minus 1. So cosine of pi over 2 minus pi over 2u minus pi over 2 is gonna be giving us cosine of pi over 2u cosine of pi over 2. So basically this is gonna be 0, and we would be having sine of, we would be having minus wait a second, no, plus, yeah, plus pi over 2 times u. So yeah, that's what we are having. Okay, and next we have done something there. We have reached up to there, and now let me just read this out once because we are having a lot of information over there. Now since our integrands are not defined at 0, wait a second, okay, so yeah, they are not defined at 0. We need to take the limit as the lower bound approaches 0, obviously, because if we talk about like obviously when you plug 0 over there, so sine of pi is it's gonna be 0, and natural logarithm of 0 is undefined. Again, for same for the this one, this integral as well. So that's why we have taken a limit as the lower bounds of each integrals as it's tending to 0. Okay, and now what okay, wait a second. We can write this as integral h to 1 of natural logarithm of sine of pi x over x and dx minus integral from h to 1 of natural logarithm of 2 over x dx. So yeah, and this integral, it's just natural logarithm of 2 times natural logarithm of x from h to 1. So natural logarithm of 1 is 0, and minus of minus natural logarithm of h. So we are having natural logarithm of 2 times natural logarithm of h over there, and we have again into u equals x over 2. Okay, so basically in this integral we have to substitute u equals x over 2, right? Okay, yeah. So we are and now we can just take a look at the integrands of each one of these integrals, and now we can combine them, because the first one is from h to 1 and the second one is from h over 2 to 1. So basically it's gonna be from, wait a second, actually this is your h and 1 and this is your h over 2. So the first one is from h to 1 and we have minus. So the first one, this is your first, so it's to h to 1, so this is your first one, and the second one is from h over 2 to 1. So basically when we just subtract this subtract 2 with 1, so we would be having from h over 2 to h, that's it. So yeah, so we are having from h over 2 to h, and yeah, okay, yeah, with a negative sign, because yeah, with a negative sign we can understand that with our previous image. Wait a second, yeah, here it is. Let me just go with this once. Wait a second, and here we are. Okay, so basically when we subtract this one with 2 with 1, so basically we, yeah, obviously because h to 1, so that's why we would be having negative. Yeah, it's kind of understandable over there. Okay, and next we have, yeah, as like since x tends to 0, so we know that sine of x also approaches to x or tends to x. So we can write this as x only. I'm sorry, pi x, because the argument is pi x. Okay, and again what, okay, so we can just split this up and we have natural logarithm of pi plus natural logarithm of x, and finally we are having this integral and this one. So this integral is kind of easy. And after solving this one, so basically, you know what, for this integral what we have to do is you have to plug natural logarithm of x as t, so we have 1 over x dx as dt. So we would be having the squared of this part of your numerator over there. So yeah, so this is the result actually. And finally, just substituting all the limits back into it, we are having, okay, wait a second. So yeah, substituting and just looking for limits, the terms containing h will cancel out, so we are only left with actually this 0, and this one is also 0. So we would be having this is your 2 cancels out, and we would be having minus natural logarithm of h. Wait a sec, wait, this is your 0. So we are having natural logarithm squared of 2 over 2, right? And plus, I'm sorry, minus natural logarithm of 2 times natural logarithm of pi. So yeah, that's what we are having so far, and this is the final result actually. Oh well, that was a lot of work. Yeah, it was actually. Okay, so this is the result actually, but when you just solve this out on a calculator, so you're gonna get the same result. And we've got another integral. Wow, this is kind of amazing. We can wait a second. Should I try this out once? Because I have got something there. I'm gonna use DI method, but for that, let me just integrate x over square root of 1 minus x squared dx, this integral. So for that integral, what I have to do is 1 minus x squared equals t squared, right? So we have minus 2x dx equals 2t dt, and here we can say x dx is minus t dt. So integral, it's minus, wait a second, yeah, minus t dt, and we have t. So basically we would be having minus of t, which is minus of square root of 1 minus x squared plus c. So this is the value of that integral, right? And now I'm just going to use the DI method, plus minus. We have to take the derivative of natural logarithm of x and integrate x over square root of 1 minus x squared, and that's why I just integrated it out. So after integrating it, we were having minus, wait a second, minus of square root of 1 minus x squared, and the derivative of this is x, right? Okay, it still it still looks terrifying, because this times that, and we are having this inside an integral. So basically this is coming out to be minus of natural logarithm of x times square root of 1 minus x squared, and plus integral, actually this is being evaluated from 0 to 1, and we have integral from 0 to 1 of square root of 1 minus x squared over x dx. And let me just try this integral out once. So for this integral, I'm just going to use x equals sine theta. So we would be having dx equals cosine of theta d theta, and our limits are gonna be from 0 to pi over 2, and we have one square root of 1 minus x squared is gonna be cosine of theta, right? And we are having cosine of theta d theta as well in the numerator, and we have sine theta, and this is coming out to be integral from 0 to pi over 2 is cotangent of theta. Yeah, it's cotangent of theta times cosine theta. It's kind of complicated, I think. Okay, yeah, let me just look at this solution. I need to just check the solution here. Okay, so basically this is the curve, right? So this is kind of you can say yeah, it's kind of parabolic. Okay, so we have to let u equals square root of 1 minus x squared, and we have the derivative or something sort of that. Okay, so our integral is now from minus times integral from 1 to 0. This minus is gonna helping us out with the interchanging of that limits. And now we are having, yeah, it looks amazing, dude. what I did here, did a mistake? I'm not sure. T is the square root of 1 minus x squared, and the integral of minus dt is just minus t, right? Because I have assumed 1 minus x squared equals t squared. So we have minus 2x dx equals 2t dt, and x dx as minus t dt, and this is the square root of t, right? So it's just t, so tt cancels out as we did here, and we're having this. So I think the integral is quite correct, but the thing is we got us stuck over here, over this integral actually. Wait a second. Though we can do that, but I think we got to use another GDI method, or we can use some trigonometric identities. Wait a second. Let me just check this out once, guys. Wait a second, guys. Let me just check this out once again. So we have assumed x equals sine theta. So square root of 1 minus sine square theta is square root of cosine square theta, which is cosine theta, right? And we have dx as cosine theta d theta. So basically it's coming out to be cosine square theta. Okay. And now what we can do here is, let me just erase this. Now we have integral from 0 to pi over 2 as cosine square theta over sine theta d theta. This can also be written as 1 minus sine square theta over sine theta d theta. Integral from 0 to pi over 2, and we have cosecant of theta d theta minus integral from 0 to pi over 2 sine of theta d theta. I think it does make sense. Hey, wait. This integral is diverging. Oh, I don't want to just get into it. Let me just go through the method of this book. So this is amazingly easy, guys, literally. But you have to just take care of this substitution because it looks amazing. The substitution is kind of perfect. Okay, and now we have your integration by parts. We know that. So we know that this is your, what we call, it's your product rule, right? I'm sorry, I was like having a difficult time to just recognize that. I'm sorry. Okay, so wait a second, let me just get a box here. Okay, so this is your product rule, right? And now integrating this, basically this, so here it is. Integrating that thing, so that's gonna be giving us something sort of this, because integrating u times v prime d, wait a second, not any, we can just integrate that because there are two functions over there. So, and then integrating u prime v plus integrating v prime u, and here we would be having vu equals your, oh wait a second, I think I'm just doing something wrong here. Okay, so this is gonna be your integral of u d, no v dv, it's v du, and plus integral of your u dv. And from here, if you isolate the integral of u dv, so that's going to be giving us integral u dv equals uv minus integral v du. So I think this is right, I'm not sure, I just did something that I have seen somewhere. Okay, I think here it is. We just have to integrate it. Okay, so and now these are some integrals which can be easily done with the integration by parts, right? So there are a couple of questions which if you want, so I think I will be discussing this very integral. Wait a second, I'm not sure, but I think I just, yeah, wait a second. So, I have got something which I'll surely try to prove this down in a separate video. And yeah, let me just take a picture of this so that I would remember that I need to just take a proof video of this one. So let me just click a picture of it. Yeah, so I'm done with this, and now I'll be just taking care of that, because with the help of this integral, this generalized integral, we can easily do this one. So okay, yeah, yeah, this looks quite amazing, isn't it? So there are a lot of integrals which you can consider if you want. And again guys, if you want any integrals solution separately, so you can just give me the you can comment down on the timestamp when you saw the integral, and I'll just take care about the solution of that integral in detail. You know what, in one of my previous videos I have proven this integral down as well, actually generalized it. So basically it's your pi over sine pi over n. You know what, I have talked about integral from 0 to infinity of 1 over, wait a second, oh yeah. I think I haven't done this, I'm not sure guys. Yeah, I'm not sure. Again, this integral looks amazing. Should we check this out once, because yeah, this is not that long actually. Let's just check this out once. So what we have to do is we have to, in order to, so if we just consider this substitution, so we have integral from 0 to, wait a second, integral, wait a second, from infinity to 0, right? Because I'm just having a look at the substitution. So we have natural logarithm of, well, this can be written as 2 times of natural logarithm, right? So we have 2 times of natural logarithm of x, which is a squared over u, over, we have a to the 4th over u squared plus a squared, right? And we have the derivative factor as minus a squared over u squared du, and minus is kind of helping us to just change the bounds. So we have 2 times integral from 0 to infinity of natural logarithm, 2 times natural logarithm of a minus natural logarithm of u, over, we have a squared plus 1, wait, a squared plus u squared du. Yeah, so here it is actually. And now what, okay, so we just have to split the integral, and this is your general integral, which is gonna be 1 over a arctangent of u over a from 0 to infinity. So wait a second, I think it's, is it 2ia, hey baby, oh wait a second. So here we had just made this integral as our original integral. So basically both of these things may mean the same. So that's how we have 2i and we have this thing. So yeah, using solving this integral will lead us to get this answer. And this chapter deals with a lot of integrals, guys, and this is amazing. This is really amazing. Just take a look at this. We did solved an integrals that looks similarly like that, but Yeah, wait a second, what we're having here. Let f of x be an even Riemann integrable function on this interval actually, and g of x an odd Riemann integrable function on this interval where alpha belongs to real number. We then have integral from negative alpha to alpha of f of x over 1 plus b to this g of x dx as integral from 0 to alpha of f of x dx. Wow, this looks amazing. Let's just take a look at the proof of this one. We have this integral, right? So basically you just have to note down that your f of x is your an even function, right? And your g of x is an odd function. So that's what you just need to note it down, because that's why it's given over there, because that's gonna be helping us out a lot. So yeah, we just have split it from negative alpha to alpha as from negative alpha to 0 plus from 0 to alpha, right? So basically, you know what, it's something sort of this. Let's consider that wait a second, actually it's wait a second, that's not the perfect curve, but you can consider it something sort of that. I'm just giving you a perspective actually. So if we talk about this part, so this is in your negative part and this is your positive part. So yeah, okay. So now what he did is he just substituted u equals x in the I1. Okay, so okay, wait a second, let me just give you an information here. When function h of x is even, then h of minus x is equals h of x, and when function h of x is odd, then h of minus x equals minus h of x. So you just have to consider it down. And you know what, our f function is even function, so basically this is gonna be your f of u only, right? Yeah, just take a look at this. Using the fact that f of u is even and g of u is odd, we have this integral, right? So what we did is we just multiplied and divided with b to the g of u. So what's that's going to be giving us is basically this is going to be 1, and we would be having 1 plus b to the g of u, and in the numerator we are having f of u times b to the g of u, that is from 0 to alpha. And now what we have to do is we have to add I1 plus I2 that we had there, and just check this out, because when we add this very integral with this one, so the numerator is just factoring out as, because they both are having the same function, so as of this one, right? And we just got rid of these two things as well. So basically this is coming out to be integral from 0 to alpha of f of x dx. This is amazingly amazing, isn't that? Okay, now let's just go further, and we are here with our exercise problems, and I think we are done with this chapter. Yeah, and our next chapter is Feynman streak. This is even more amazing. And guys, you know what, in one of my previous videos I have discussed 4 integrals using the Feynman streak, that was differentiating under an integral sign. So basically this Feynman streak, I think it says differentiating under integral. So that's what it deals about, as far as I know. But we'll get to know a lot of things when we talk about this chapter in our next video. So for that case, I think it's done, and this video is also ways of 1 hour, right? So yeah, for that's it. I hope guys, you got to learn something out of it, and if you did, please make sure to like, subscribe, and share. And yeah, I'll be bringing a lot of things like this, and I'm thinking to just prove that down, because I have announced that I have to prove an identity that we saw in this chapter. Where it is, let me just, oh wait, yeah, wait. Yeah, here it is. I think this one. Yeah. So this integral. So this looks amazing, and this is kind of good generalization. So for that case, maybe it's gonna be our next video. But we have two things to do in our next video. The first one is to this one, and the second one is to talk about the third chapter, that is the Feynman's trick. So let's just see which one I'm just gonna consider first. But surely we'll bring both of these things one by one. Yeah, so goodbye guys, take care, love you, love your life, enjoy, do whatever you love, but be careful what you're gonna do, because loving doesn't mean you will get everything like healthy, right? So for that case, I love you guys, goodbye, take care, just stay tuned with me. i'll get you I'll get to you a lot of things which most probably you will thank me for. Okay, so it's 30.